This video is going to continue looking at reactions of alcohols as well as ethers. Last video ended up talking about dehydration. We underwent some reactions with tertiary, secondary, and primary alcohols. The tertiary ones are going to be the easiest to dehydrate, and you should realize why that is. Tertiaries are going to make the best carbocation, so it's going to be the easiest to make that OH group leave. Dehydration of a secondary alcohol is still going to go an E1 mechanism, and this will be the same steps that we saw in the last video. Notice here we have two options of where the double bond can be made in addition to having cis or trans. So we would have the acid protonate our OH group giving us our carbocation, which, since there's no good nucleophile around, it can undergo elimination. Look at this product distribution. You can see that our more substituted bond is a very major product, our less double bond only coming in at 3%, and of that major product we're seeing trans being overwhelmingly favored, which makes sense what we've seen with other elimination reactions. So you're always going to see that the trans product, where you're seeing your groups being on opposite sides, since they're more stable, being your major product. What would the mechanism look like? Very similar to what we talked about in the last video, where our OH group is going to pick up that hydrogen. Since this is going to be an E2 reaction, it's going to happen in one step, where our base would come in, take the hydrogen, and kick off that leaving group. Here you would have only one possible product. With primary alcohols, you actually do have competition, so you will see some SN2 reactions depending on what the nucleophile would be. Remember here, where is this ethanol coming from? It is our starting material, so it's likely that that would also still be there. If you have substitution, you would then make a protonated form of an ether, which would then be deprotonated to give you your neutral ether as a substitution product. So again, here you would have both E2 and SN2 products being obtained because it's a primary unhindered position where you can push these depending on the reaction conditions. The next part of reactions we're going to talk about with alcohols involves oxidation or reduction reactions. Oxidations reactions are ones that are increasing the number of CO bonds, whether that's via a single bond making an alcohol, or whether that means two bonds making a carbonyl. In this case, this would be an aldehyde, or furthering it, making go from 2 bonds to oxygen to 3 bonds. So again, oxidation, we're saying increasing the number of bonds to oxygen. Reduction would be the reverse. So if we have an alkane, we can turn that into a secondary alcohol. In this case, we have R prime, meaning other carbons. Here we can eliminate hydrogens, but we cannot eliminate carbons, so a secondary alcohol could be oxidized, as a tertiary carbon would not be able to oxidize further than making a tertiary alcohol. So we'll go through some different reagents looking at how we can oxidize alkanes or alcohols into these other carbonyl compounds. So we'll start with the primary alcohol. A lot of these chromium reagents usually have two names. You're going to see one's named as Jones, and you're going to see one's named PCC. The formulas that you see up here are a wide variety of different chromium compounds. But if we use a chromium compound, this is again something you'll see listed as Jones with a primary alcohol. It will oxidize, and notice here this is in brackets, meaning it's a transition state, so it will oxidize even further to a carboxylic acid. If you use Jones, that you will get a carboxylic acid. If you use a different chromium reagent known as PCC, you will end up oxidizing a primary alcohol to an aldehyde. This reagent is different in that it will stop at the middle stage of what Jones can do. You do not need to worry about the mechanisms of these, but you should be able to associate what functional group you're starting with and what functional group you're ending with. In both of these cases, primary alcohols can turn into carboxylic acid or aldehydes depending on which reagent you use. For secondary alcohols, again, notice the bottom, these are two different chromium reagents. Top one known as Jones, the bottom one sodium dichromate. And here, if you're seeing chromium and you're not seeing PCC listed, you should associate that as oxidizing as many hydrogens as possible. Since it's a secondary, it's only going to be able to remove one hydrogen away from the carbon that's attached to the alcohol. So both cases here, these will turn into a ketone and a ketone on the ring. So secondary alcohols will always go to a ketone. And again, don't need to worry about these mechanisms either. Tertiary alcohols cannot be oxidized because there's no hydrogen to remove. So there's no way to make an extra bond from that oxygen to carbon without having to remove a methyl group, which will not be favored. So tertiary alcohols, any type of oxidizing reagent, should be no reaction. The other oxidizing reagent, and this is where the mechanism will come into play, will be hypochlorous acid. And hypochlorous acid actually will give two different products depending on whether you have a secondary alcohol or a primary alcohol. If you have a secondary alcohol, it will oxidize to a ketone. If you have a primary alcohol, it will oxidize to an aldehyde. And we'll talk about how this happens here. Your first step, just like we saw with other acid mechanisms, is you're going to protonate your OH group on your ring. This is going to give you your good leaving group. The only thing tricky about this mechanism is that it does involve a drawing in SN2 mechanism at a secondary position. This works because the anion here is actually very nucleophilic, and you still have a really good leaving group at that position. At this point, you have the OCl bond, and that OCl bond is going to actually be very weak. You can have a base remove the hydrogen off of that position, creating your carbonyl. I'd say these steps 2 and 3, these arrows are a little unique for this. What I'd encourage you to do is associate seeing hypochlorous acid as your oxidizing agent, and what do you need to do in order to make a double bonded oxygen at that position, whether it's an aldehyde or ketone. And there's only one way to do that. The base cannot come from any other carbon other than the one that it's attached to the oxygen. The next thing we're going to talk about is ether nomenclature, where you're going to be treating your ether as the main functional group, just like you would with an alcohol. They have new names for them. Think of it as a methyl group, a CH3 group, with an oxygen on it, so it becomes methoxy. An ethyl group with an oxygen becomes ethoxy. And we're going to treat those just like an alcohol with this new substituent name. So for the top left, we have a 4-carbon chain with an ether on the second position. So it would be a 2-methoxybutane. For the one on the right, we have an ether on the 1 position. Our longest carbon chain would be 5 carbons. So we would have a 1-ethoxy 3-methyl pentane. Pause the video and try to complete the bottom 2 on your own. Okay, so for the first one, you're again looking at which side of the ether is longer. On the left, we have our shorter side, so it's going to be a butoxy group. It is at the 1 position. Notice your carbon chain is going to be starting at the 1 from there, so your methyl groups would then be at the 2 and 3 positions going towards the right. Here we have a diether with both of the groups being the same, so we would treat it just like any other functional group. You can match this one to the top of the screen, and we have a diisopropoxybutane, and again at positions 1 and 4, it doesn't matter if you go left or right, you get the same set. The reactions for ethers are exactly the same as alcohols. This is still going to be a poor leaving group, whether that's an OH or an OR minus. And so in order for these to react, it's going to need to be activated again using acid. So once we add the hydrogen to that ether, we have a good leaving group. With heat, we can then have that group kick off with our iodine acting as the nucleophile. The mechanism for this is going to look very similar. You're first going to go out and grab your hydrogen from your acid, kick off your nucleophile. At that point, you can have a leaving group. Remember, this is a tertiary position, so it's going to be an SN1 mechanism, meaning you will have your carbocation being formed. Notice here at this step, I also have generated some methanol, which was our leaving group. So you want to make sure if you have to draw this mechanism out, you're including both of those pieces. In the end, we've added our nucleophile, replacing our iodine where our methoxy group was. If it is a primary ether, meaning both of these carbons are going to be primary carbons, your mechanism actually is going to look a little different. Your starting step, your first step, will still be the same with your oxygen picking up a hydrogen, creating a good leaving group. In this case, since both of those carbons are primary carbons, you're going to have an SN2 mechanism. Remember, your nucleophile is going to attack at the less hindered position, meaning it will attack the methyl side of your ether rather than the propyl side in this example. Again, with ethers, make sure you're counting both pieces. So here I have my methyl group with an iodine on it, and my other piece was my original longer chain from my starting material. Here it is propanol. So if you cannot make a stable carbocation, it's going to be SN2. Remember where your iodine will go. It will add to the smaller carbon piece of your ether. And if it is not a primary, meaning if you have a tertiary or secondary, you will be able to undergo an SN1 mechanism.